In this video, we present an out-of-distribution detection algorithm called ViM, namely the Virtual-logit Matching, which has a superior performance on large-scale OOD detection problems. As shown in the picture, given a classification network that distinguishes crab and cat, when new images such as dogs or clapping hands are given as inputs, it will mistakenly recognize the images to the class it knows. OOD detection equips the network with the ability to decide whether an input belongs to the training distribution. It can be applied to a wide range of applications such as autonomous driving, medical analysis, and industrial inspection. OOD score is used to indicate to what extent the sample is likely to be an OOD. The commonly used evaluation metrics are the AUROC and the FPR95. Researchers have designed OOD scores taking advantages of various information sources, including the probability, the logit, the features, and others. The information of probability, for example, has MSP and kill matching methods. The logit has max logit and the energy methods. Methods computed from features include Mahalanobis and News scores. And there are also methods taking advantages of gradient information, and so on. These methods, including our newly introduced ViM method, neither require retraining the network or need extra OOD data labeling, making their deployment effortless. Also, there are methods that need retraining or extra OOD data. For a typical network, some dimensions are dropped going from feature to logit. In this figure, we find that feature-based methods such as residual and new-saw are better at texture dataset, indicating that the dropped class agnostic information is used for OOD detection. Contrastingly, logit and probability-based methods are better at iNaturalist, showing that the class-dependent information is also helpful for OOD detection. This leads us to the critical question of how to combine OOD evidence from feature space and those from logits. To unify the class-agnostic and class-dependent information for OOD detection, we propose an OOD score named the Virtual-logit Matching. The pipeline includes 3 steps, operating at the feature, logit, and probability respectively. For input feature X, we first extract the residual XP_perp against the principal subspace P. Then we convert the norm of XP_perp to a virtual logit by rescaling. Finally, we output the softmax probability of the virtual logit as the ViM score. The greater the ViM score, the more likely the sample is an OOD. Here are the details. We define virtual logit as the rescaled norm of the feature X projected onto a given subspace S, and that's the tool to combine OOD evidence from feature space and those from logits. The subspace we use is the orthogonal complement of the principal space P. The scalar alpha in the second equation is defined to match the scale of virtual logit to the original logit. And finally, the ViM score can be written as the third equation. We can see that larger virtual logit L0 or small original logit Li both leads to a larger ViM score. All makes sense because a larger ViM score indicates a larger probability of being an OOD. We built a new OOD dataset called OpenImageO for the ID dataset ImageNet1K. It is manually annotated, comes with a naturally diverse distribution, and has a large scale with more than 17,000 images. It is built to overcome the shortcomings of the existing OOD benchmarks. OpenImageO is selected image by image from the test set of OpenImage v3. Compared to the ImageNet-O, OpenImageO has a wider class coverage as shown in the figure, and is harder to hack. As we can see from the experimental results, ViM performs better than the single information source-based methods on both OpenImageO and ImageNet-O. We tested 4 OOD benchmarks, and ViM is the best on average. We also tested more model structures, including CNNs and vision transformers. ViM performs consistently well in all kinds of networks. To know more details, please find the resources here. Thanks for watching.